comes on, they decrease their firing rate. And some do both, depending on the type of stimulus. The excitatory neurotransmitter, mostly glutamate in the central auditory system. The inhibitory neurotransmitters are mostly glycine and gamma aminobutyric acid. We talked about a second type of functional difference. Remember that all primary auditory nerve fibers have that same response when a sound turns on. They have that initial bump up, spike in responding, and then they go steady state. Then when the sound turns off, they drop their response below their spontaneous rate, and then they move back to their spontaneous rate. But in the central auditory system, you have some of those, but you also have funky response types, cells that only give you a burst of responding to the onset of a sound, cells that only give you a burst of responding when a sound turns off, called off cells. We have chopper cells. We have pauser cells, cells that'll give you a burst, and then they take a rest while the sound continues, and then they start up again. And so different types of cells in terms of their functional response. We talked about rate level functions. Remember, this is the response of a cell, of a nerve fiber, to changes in the intensity of the stimulus. And remember that in the auditory nerve fibers, we have the same kind of response from every fiber. They all cover about a 50 dB dynamic range, and over that range, they increase their firing rate up until they reach the limits of their dynamic range. They don't all have the same 50 dB range, but they all have about a 50 dB range. In the central auditory system, some rate level functions are going to be smaller. They won't cover as big a range. Some of them will be larger, and some of them will be non-monotonic, which means they might increase their firing rate to increases in stimulus intensity, and then as you keep increasing intensity, they might decrease their firing rate. And then finally, some cells that may only respond to very complex inputs, like cells that won't respond to a pure tone, but they might respond to an amplitude modulated tone. So cells that might only respond to very complex inputs. So those were the main structural and functional differences. And they're important because the structural differences, for example, if you think about those different cell types, they're going to allow you to do different kinds of communication up the food chain. And let's draw a couple just to give you an idea. So let's go ahead and share our screen, and we'll go to the whiteboard. So imagine here is a stellate cell. So here's its nucleus, here's the area around the nucleus, but then it's got these long projections off in various directions like a star. So it's going to communicate primarily with other nerve fibers that are kind of far away from where the nucleus of the cell is. Whereas if you've got a cell like a bushy cell or a globular cell, and it's got a whole lot of projections, but they're very short projections, then the communication of this cell is going to be primarily with other fibers that are very close by, and maybe a lot of them. The stellate cell may have fewer total connections. The bushy cell might have more connections, but this is going to allow you to do very different kinds of processing of the sound, because this cell is going to talk primarily to its immediate neighbors. This cell is going to talk to faraway cells. So that's how cell morphology can give you the opportunity to do additional processing of the sound. In the same way, on the functional side, some of these different types of response that you get out of these neurons, if you've got one cell that's doing something kind of like the primary auditory nerve fiber, but you've got another cell that only responds to the onset of the sound, and say that this response type is connecting to a cell that has that response type, then you're going to get some filtering of sound information as you transmit information from this cell to this cell. So both the structural and the functional differences give you the opportunity to do different additional processing at different levels of the auditory system. Okay, let us stop sharing that. Then we started talking about the specific way stations on the way up, and we started talking about the cochlear nucleus. Remember, we said that the cochlear nucleus has 3 different areas, and each of those areas has its own tonotopic representation of frequency. So there's the anteroventral cochlear nucleus, the posteroventral cochlear nucleus, and the dorsal cochlear nucleus. And each one of them has its own tonotopic representation. And remember, we showed you the infamous parsnip diagram. So here is the parsnip diagram. Let's see if we can get to the slideshow. There we go. Oops, wrong one though. So this was the one, and it's a little bit hard to see, but here are all the high frequency neurons coming from the base of the cochlea. Notice where they project. Here is where they project in the anteroventral nucleus. Here is where they project in the posteroventral nucleus. And then down here is where they project in the dorsal area of the cochlear nucleus. Middle frequencies in the middle of the cochlea are coming in here in the anteroventral cochlear nucleus, over here in the posteroventral cochlear nucleus, and down a little further in the dorsal cochlear nucleus. And then finally, if we look at basal neurons over here, what we're going to get are projections still further up in the anteroventral cochlear nucleus, still further up in the posteroventral nucleus, and further down in the dorsal cochlear nucleus. So if you look at it together, high frequency, mid frequency, low frequency. And so you can see that the tonotopic organization in the cochlear nucleus is determined. That gives you at least the suggestion that in the cochlear nucleus, the different areas, the anteroventral, the posteroventral, and the dorsal, are perhaps doing different things as they code frequency. All right, let's stop sharing that for a moment. Okay. And then I want to show you a different figure. Let's find it. This one. So I will never ask you about this, but I just wanted to show you, if you look at, this is now upside down. Here's the anteroventral cochlear nucleus, here's the posteroventral cochlear nucleus, and here's the dorsal cochlear nucleus. These are the different cell morphologies that you see in different parts of the cochlear nucleus. So notice, for example, number 6, stellate cells are found in the anteroventral and posteroventral cochlear nucleus, but not in the dorsal cochlear nucleus. So why do we care that stellate cells might be found here, but not up here? Well, remember what we said about the way that the cochlear nucleus connects to other parts of the central auditory system. Remember we said that there are connections to the superior olivary complex on the same side, ipsilateral, connections to the superior olivary complex on the other side, contralateral, and connections to the inferior colliculus on the opposite side. Well, in order to get to the inferior colliculus on the opposite side, that's a pretty long stretch. You need something like a stellate cell to do it. And so the projections that go contralaterally and skip the superior olive and go all the way up to the cochlear nucleus are almost entirely coming from these stellate cells. And the stellate cells are found in the anteroventral nucleus and the posteroventral nucleus, but not in the dorsal cochlear nucleus. Another piece of information that suggests that these three areas of the cochlear nucleus are perhaps doing different things. Similar situation with things like octopus cells that tend to have kind of long, stringy projections. But up here in the dorsal nucleus, these are tinier cells in terms of their projections. They don't project as far. So that is interesting. And again, some indication that perhaps the different areas of the cochlear nucleus are doing different things. Okay, so what do we think is going on? Well, one of the things that seems to be true in the cochlear nucleus is that the dorsal cochlear nucleus is especially sensitive to frequency. It seems to be very responsive to fine frequency discrimination and spectral shape and those kinds of things about a sound. Whereas timing information is probably better in the anteroventral cochlear nucleus and to some degree in the posteroventral nucleus. So what do we think is actually happening in the cochlear nucleus? Well, frequency discrimination, the tuning curves look about like they look in the primary auditory fibers, right? So the tuning curves are kind of the same. There is some evidence in terms of frequency for something called lateral inhibition. So lateral inhibition, and let's go back to the whiteboard, because lateral inhibition is actually an important concept. So lateral inhibition. Lateral inhibition is kind of what it sounds like. Lateral means sides, and inhibition means reduction in firing rate. And so what's happening is that responses in nearby cells decrease the firing rate of the cell, the main cell, right? So you've got all these nerve fibers. Remember that in some areas of the cochlear nucleus, like in the dorsal nucleus, most of those fibers are, the cells that are there are small projection length. There might be bushy cells or globular cells that have a lot of projections, but they don't go very far. And they may be responsible for some of the lateral inhibition that is taking place. So what's the effect of lateral inhibition? Well, remember that down in the cochlea, we talked about the fact things like two-tone suppression, for example, that you've got these different fibers and their tuning curves. Here's one, but remember there's one right next to it that has a different tuning curve, and there's one right next to it that has a different tuning curve. And you can get these areas, if this is your main one right here, you can get these different areas where you get two-tone suppression. But what seems to be happening in the cochlear nucleus is when you get into the response areas of these nearby fibers, they cause a decrease in the firing rate of your main fiber. Well, what does that do? The effect of that is that you get better frequency discrimination because the cell becomes much more selective to frequencies that don't stimulate those nearby cells. So again, if you've got, there's a tuning curve, there's another tuning curve, there's a third tuning curve. If you're in this area right here with your information, you're probably not going to be activating this cell or this cell. And so what it means is the number of frequencies that this particular fiber responds to gets more limited to a narrower area. So what does lateral inhibition do? It probably improves frequency discrimination. At least in the dorsal cochlear nucleus, that is probably what lateral inhibition is doing, is improving your ability to discriminate frequency by limiting the range of frequencies that a particular fiber has an excitatory response to. So these are nearby fibers that when they start firing, they decrease the firing rate of your main auditory nerve or your main nerve fiber. So lateral inhibition is a way of sharpening your frequency response. And it looks like a lot of that kind of activity is going on in the dorsal cochlear nucleus especially. It is also the case in the cochlear nucleus, and this is true in the anteroventral and posteroventral areas, that there are some cells that are very sensitive to very small intensity differences in a sound. So if you have two sounds that have a very small intensity difference, or you have one sound that changes its intensity in a very small way, you have some fibers in the anteroventral and posteroventral areas of the cochlear nucleus that are selectively responsive to very small intensity differences. So the fact that you've got some fibers that are sensitive to very small intensity differences suggests that those fibers are playing a role in intensity discrimination. Remember back Weber's law, what's the smallest difference in intensity of two sounds that you can tell that they are different? That also turns out to be important for something we're going to be talking about at the next way station up the way. So we know that the cochlear nucleus gets all this input from the cochlea. We know that particularly in the dorsal nucleus, there's a lot of frequency coding going on. We know that the anteroventral and posteroventral areas are very sensitive to timing differences, very good timing sensitivity, and very good intensity discrimination. We also know that the projections up the food chain, so the dorsal cochlear nucleus is going to project to the superior olivary complex, but probably mostly on the ipsilateral side, whereas the cell types that we find in the anteroventral and posteroventral cochlear nucleus have the length of projection that they can project to the contralateral superior olivary complex and to the contralateral inferior colliculus, skipping the superior olivary complex completely. Okay, I'm going to stop there and ask if there are any questions. Would I be able to type out what I just said? Well, yes, Ava, I probably can, although that would require me to remember what I just said, which as I say things, they just kind of come out because, as you know, I tell stories. So what did I say? I said dorsal cochlear nucleus, globular and bushy cells, short projections. So probably what that means, and I'll show you why in a second, probably means that it projects ipsilateral, the superior olivary complex, possibly contralateral to the superior olivary complex. Good frequency coding. Also lateral inhibition, which helps us sharpen frequency discrimination. Anteroventral and posteroventral. They also have some of these globular and bushy cells, but they also have stellate, octopus cells. These have long projections. It probably is ipsilateral projection to the superior olivary complex and contralateral. And good temporal coating and excellent intensity coating. So probably plays a role in intensity discrimination. I think that's everything I said. That's most of it anyway. Okay, so everybody good with that? More in the chat. What do we got?
She just said she said thank you, this was very helpful.
Okay. Okay. I will, I'm going to stop sharing this if everybody has it. And I will share something different that explains why I said what I just said. So where do we want to go? Let's go here. This one probably shows it just as well as anything else. So coming out of the cochlea, primary afferents come into the cochlear nucleus right here. They project ipsilaterally to the superior olivary complex, which is this structure right here. Notice how close it is. So a cell like a globular or bushy cell might actually be able to make that projection. Contralateral to the superior olivary complex on the other side, but then also a contralateral projection that goes all the way up to the inferior colliculus, right? So that's why you're going to need a stellate cell. It's kind of a long way to travel to get from the cochlear nucleus all the way over across the midline up to the inferior colliculus on the opposite side.
Dr. Weisenberger, we can't see your screen.
So that's why. Now I'm looking at all of this and I am not seeing that it is sharing. So hold on a second. All right, I assume you can see it now. Sorry about that. So here's auditory nerve fiber, cochlear nucleus. Ipsilateral superior olive is very close to it. Contralateral superior olive isn't all that far away, but the inferior colliculus on the contralateral side is a really long way away. That's why you need those stellate cells, and that's why the AVCN and PVCN probably are responsible for any connections that go directly up to the inferior colliculus on the contralateral side. Those smaller cells, like globular and bushy cells, can make this short hop, but they're not going to be able to make the long hop. All right. The next place I want to talk about is the superior olivary complex. So we're going to leave the cochlear nucleus. Remember that there are projections from the cochlear nucleus to the ipsilateral superior olivary complex, the contralateral superior olivary complex, and the contralateral inferior colliculus. So when we get up to the superior olivary complex, we find that there are two main areas in the superior olivary complex. let's go back to the whiteboard. So I'm going to get rid of this. And we are going to talk about the superior olivary complex. So one of the things to know about the superior olivary complex is that these structures are fairly tiny. They are hard to get at and a little bit hard to record from. So we have some information about what's going on there, but we don't know everything yet. But we do know a couple of things. So we talk about two areas of the superior olivary complex, the medial superior olive and the lateral superior olive. Now, there are also some additional pieces and parts that are close to the superior olive, like the trapezoid body. We're not going to talk about those specifically in this course. If you want to know about the role of things like the trapezoid body, you're going to have to take the advanced course. But there's an interesting thing about the medial and lateral superior olive. And remember what we said, there are both ipsilateral and contralateral projections to each superior olivary complex, the one on the left side and the one on the right side. And those ipsilateral and contralateral projections go both to the medial superior olive and the lateral superior olive on both sides. So ipsilateral and contralateral projections. This turns out to be really important. So the inputs to the superior olivary complex are both ipsilateral and contralateral. The importance of this, the fact that the projections are ipsilateral and contralateral, is that, remember we said that in processing the location of a sound, that's why you need two ears instead of one, and that the auditory system is always comparing information between the left ear and the right ear. It's always an interaural difference that the auditory system is looking at to localize a sound in azimuth. And so remember what we said about all of that, that for low frequency sounds, the physics of the waveform are such that you can generate an ongoing phase difference between the two ears if the sound is low in frequency. For example, 500 hertz, assuming a head of a particular diameter, a 500 hertz sound that hits this ear first in 0 degrees phase, keeps traveling in 0 degrees phase around to this ear, will have continued on to become 180 degrees phase in the other ear. Biggest phase difference between the two ears you can get. Well, in order to do any sort of binaural processing, you've got to have a structure that's getting inputs from both ears. This is the first level in the auditory system that is actually getting both ipsilateral and contralateral inputs. So it's the first level of the auditory system that could possibly do any kind of binaural processing. Okay, so now remember what I just said about the cochlear nucleus, that the anteroventral and posteroventral nuclei, or areas of the cochlear nucleus, have good timing sensitivity, and they also have really good intensity sensitivity. And where they project in the cochlear nucleus turns out to be interesting, because the medial superior olivary complex turns out to be especially sensitive to interaural phase differences. Most of the inputs to the medial superior olivary complex are low frequency fibers. Makes sense, right? And fibers that have exquisite timing sensitivity, because remember, time and phase are kind of the same thing. So if you're going to have areas in your brain that are particularly sensitive to interaural phase differences, they have to get inputs from below, both ipsilateral and contralateral, that are really, really good timing information and selected for low frequencies, because those are the frequencies for which phase differences makes a big enough change between the two ears. So that's the kind of input that's going to the medial superior olive, right? It's got to be fibers conveying low frequency information and good timing sensitivity. Interestingly enough, the lateral superior olivary complex appears to be specialized for processing interaural level differences. And in order to process interaural level differences, remember that those are best for high frequency sounds, because the level differences are best generated when a high frequency sound hits the first ear. Remember that a lot of the sound energy that would travel onto the second ear is going to get absorbed by the head. And so you generate a head shadow between the two ears, such that the level of the sound that reaches the second ear is lower than the level of the sound that reaches the first ear. So what you need in the lateral superior olive, first of all, is high frequency information. Because remember, the high frequency sounds are the ones with short enough wavelengths that they cannot bend around the head. They are then subject to the head shadow. And fiber inputs that have good intensity discrimination. I cannot type today. Good intensity information. So when we think about the cells in the cochlear nucleus that are projecting into the superior olivary complex, this is how those projections are probably going. From the dorsal cochlear nucleus, frequency information, low frequency information going to the medial superior olive, high frequency information going to the lateral superior olive, some frequency information coming from the AVCN and PVCN as well. But then those cells in the AVCN that have really good temporal sensitivity, probably projecting mostly to the medial superior olive. Those cells in the cochlear nucleus that have really good intensity sensitivity, probably projecting mostly to the lateral superior olivary complex. This, of course, is an oversimplification of what's actually going on in the superior olivary complex. But for our purposes, this interpretation of those fiber projections makes sense. And so we actually see in the superior olivary complex some pretty interesting fiber responses. So I'm going to stop sharing this for a minute, and I'm going to show you a different picture. So bear with me for a sec while I find it. Let's see, is this where we're going to find it? Yes, there it is. Okay, so let us proceed to share that. Hang on. All right, so here is a figure that shows the response of a particular fiber in the medial superior olivary complex. And look at how its firing rate changes as you create a phase difference between the two ears. That's what this delay thing is. That creates a phase difference between the two ears. And so what you're doing is you're getting binaural inputs to the medial superior olive, and you've got a fiber in the medial superior olive that's getting both ipsilateral and contralateral fine timing information and look at how its response changes as you shift the phase difference in one direction or the other. First, you get an increase in firing rate, and then you get a decrease in firing rate, and then you get an increase in firing rate, and then you get a decrease in firing rate. So these fibers, remember I said some of them have very complex response types. This is an example of a pretty darn complex response type, right? It doesn't just always fire more in response to an input. It responds preferentially to intraoral phase differences, and it likes some particular phase differences a lot more than others. It likes ones where its response rate is maximized, and it may also like them where its response rate is minimized, because remember that inhibitory information is important too. So this is a cell that does both excitatory and inhibitory responding, depending on the different intraoral phase that it might be getting as input. So you can see how a cell like this is starting to help us process localization in azimuth. So in fact, we talk about different cells in the superior olivary complex. We're going to go to text. So remember we said some response types in the central auditory system can be excitatory, inhibitory, or both. Cells in the superior olivary complex could be what we call excitatory, meaning that they will fire more in response to an ipsilateral input and more in response to a contralateral input. We have some that are called EI, excitatory to a contralateral input and inhibitory to an ipsilateral input. The opposite of that, inhibitory to a contralateral input, excitatory to an ipsilateral input, and then ones that are just plain inhibitory to everything. So these are response types of cells in the superior olivary complex. And what that tells you is just like that figure I just showed you, which was an example of, I don't know if it was an EI or an IE, but one that did both excitatory and inhibitory responding, depending on the size of the phase difference that was reaching that cell. Okay, question.
Yes. So I had a direct message asking what were the 3 connections from the.
Oh, wait a minute, Jesse, I can't hear you.
Oh, shoot. I wonder why.
Yeah, keep trying. Let's see if I can read it.
Are you on mute, maybe?
Oh, I said the first letter was contralateral and the second letter was ipsilateral. This is something I would never actually ask you, which one was contralateral and which one was ipsilateral. But just know that there are all these different types. Some are excitatory to everything. Some are inhibitory to everything. Some go either excitatory or inhibitory, depending on the type of input that they get. Okay.
Now,
All right, any other questions? So we know that clearly, really, I still can't hear you. Wait a minute, let me try something else. Jesse, say something now.
How about now? Can you hear me?
Nope, I still can't hear you. It's all right. We can make this work.
Yeah, hold on. I think it's
all right. So we know that binaural processing. Yeah, my volume's way turned up. Don't worry.
Okay.
That was what I was just doing, was cranking it up, and I pulled my earbuds out. I put my earbuds in. Yeah. I love Zoom, probably as much as you guys all love Zoom. Okay. So, it looks like the superior olivary complex is very much specialized to process binaural information. it also preserves the frequency information that came up from the cochlear nucleus, right? It doesn't lose that information, but it doesn't seem to do a lot of additional processing